Okay. All right, so.
The distance from the center.
Yes. Okay. I started off trying to just jump right in and teach this. First period kind of flopped a little bit. It was okay. A little bit of a flop. Third period was better, but there were still some misunderstandings. So I'm going to start at the end and try and really see if I can get this clear before we get into the problems, all right? So, in the past, we had PVA. Now, the position, velocity, acceleration that we had in the past was linear motion. It was either vertical or it was horizontal, but it was always straight line, one directional, right? So one dimensional. So if we had something moving, it was either moving straight up and down or straight left and right. Usually it's like on a tightrope or on a whatever, right? So some kind of linear motion. So your position, pretend it was horizontal motion, your position would be x of t. Your velocity is x prime, your acceleration is x double prime, or v prime, right? So derivative position is velocity, derivative velocity is acceleration. That hasn't changed. That's all the same. And one of the things, it's funny, the one thing that has caught people, that people have been most confused on, is understanding that x prime of t and dx dt are the same thing. So they really are. It's just notation. Okay, so x prime of t, dx dt, interchangeable terms. Is that okay? Good. So, no, because this should all be old. All right, but I'm about to show you new.
Okay, are there any new lessons today?
Yeah, vectors. Vectors. Okay. If I could turn, I can't do this, guys. You have to be with me. Okay. If I could turn back time, now that I know what I need you to know, I would have revamped the whole parametric lesson and done it in this context, not in the context that we did it. Because the context that we did it in was a lot of pre-calculus, a little bit of calculus, and really every question that I have seen on every AP exam I've looked at so far, and I've looked at like the last 10 years so far, every single one of them is in the PVA context. And all they're doing for parametrics is they're taking position, velocity, acceleration, and instead of just doing horizontal or just doing vertical, they're writing it as a vector and doing both at the same time. All right? So you get a horizontal component and a vertical component. Okay? So it's it's the exact same PVA. The only difference is that now your position has an x of t and a y of t, and it'll be written as a vector. All right, so your velocity is going to be x prime, y prime. You just do them separately. You just treat them separate, you do them separate. All right, you have the rate of change of the horizontal motion, you have the rate of change of the vertical motion. Which again, x prime, y prime is the same thing as dx dt, dy dt. And then acceleration is just x double prime, y double prime. So it's the same thing we've been doing. The only difference is that now we get to take what it was once just linear motion and we can make it two-dimensional. Okay? All right, so now, so that's where we were, this is where we are. I'm going to go back to the beginning screen. So, quick reference, PVA with vectors. So you have a position vector, x, y. You have a velocity vector, x prime, y prime. You have an acceleration vector, x double prime, y double prime. This is some new stuff. Speed. Speed is the magnitude of the velocity vector. A vector, you guys, I know you know this. A vector has magnitude and direction, right? Direction and magnitude, right? Okay. So,
You played us a clip.
okay. Alright, so anyway, magnitude. So, the magnitude is basically like how much velocity there is. So if you have a velocity vector, that means that, say I'm going, like that's 0, say I'm going, pi 6 this direction, and I'm traveling at 45 miles an hour. So I would have a length of 45 and a direction of pi 6. So that's velocity as a vector. So speed, and that doesn't really come into play in these problems. It's not your traditional vector where you're like lining tip to toe and finding a resultant vector, all that kind of stuff. That's not really what they're doing. All they're doing is using vectors to separate velocity into horizontal and vertical components. That's all they're doing. So your speed is the length or the magnitude of the velocity vector, which is truly just Pythagorean theorem. Remember, if the length of the velocity vector, if you call that v, you have an x, you have a y, x squared plus y squared equals that squared, right? So your speed is the square root of x prime squared plus y prime squared. Distance is the definite integral of the absolute value of velocity. What is the absolute value of velocity? Well, that's speed. So distance is actually the definite integral of the speed, which in this case you would use this function for your speed. So, PVA problems on the BC Calculus exam usually are written as parametric equations in vector form. I'm trying to emphasize, the math doesn't change. The only thing that has changed is the format. Now you have little corner brackets and you have an x and a y. Everything else is the same. One other little thing that they like to throw into these problems, which is the only thing we actually did that relates to these when we were doing our parametrics, is if they ask you for slope, slope is dy dx, right? Not dy dt, not dx dt, it's dy dx. So if they ask you for slope, remember that's just dy dt over dx dt, right? So if you have a velocity vector and they say, hey, what was the slope of that function at t equals 2, you could just take whatever's here over whatever's here, right, and plug in a 2. So, alright, we're going to slowly walk through 2 problems together. Then I'm going to have you guys work on your own on another problem or 2, and then we'll be done.
You haven't checked the homework.
I know, I'm going to check homework when you guys are working independently. That's what's worked well today. Because I didn't have I tried to have a warm-up and it didn't.
What did
go
you
well.
do? What have you done to the computer people? I don't know which one of you it was. It was either him or it was you.
That wasn't me.
How nice is it?
Was it you?
It's good. You can see it.
It's still fun.
Yeah.
Alright. Is it framed still?
Yeah, it's so
we're
good.
Okay, alright.
Who you texting, bro?
So, the first problem we're doing is last year's AP exam, number 2. Okay? So, less than a year ago, students were sitting in the small gym working this problem. Okay? You can only hope that you have a similar one this year.
Or you can hack into the college board and find out.
Yes.
Probably not. I don't know. Go for it.
What does we have?
Alright. Okay, so here we go. Let's read through this. At time t greater than 0, a particle is moving along a curve, right? Before it was always a line, now it's a curve. So particle is moving along a curve in the xy plane that has position x of t, y of t, with velocity vector v of t equals this. Someday when I retype this problem, I'm going to put the v of t and make sure it's over here. So this is v of t. V of t, in case you have forgotten, is x prime y prime, or dx dt, dy dt, right? Okay, all right, good. At t equals 1, the particle is at the point 3, 5. Now, part A, this it's the same, you know what, I think I'm going to do part A on it. Well, no, it's okay. All right, part A gets asked a lot. It got asked a lot on the old PVA problems. And there were, even if we were doing the old PVA problems, people would miss part A because people just forget how to do this. So I'm going to walk you through and remind you how to do this type of problem. So if we have velocity and we need position, how do we find it? We need to integrate. Now, in the olden days, back in the 70s, 80s on the AP exam and 90s, you would find the antiderivative with a plus c, and then you'd take the given point, which is 1, 3, because we're just talking about the x-coordinate. So we take the given point, plug it in, solve for c, have a position function, and then plug in the new point and get the position at that time, right? In the 2000s, the College Board made a decision that they decided they wanted to really promote the first fundamental theorem of calculus. And the first fundamental theorem of calculus, of course, is all about definite integrals, right? So what they started doing was they started asking the exact same questions, but they gave you functions where you couldn't anti-differentiate them, like cosine t squared.
Well, that's annoying.
Yeah.
Well,
Why?
even is anti-differential.
Okay.
Can you do the by parts?
Can I plug it in on my calculator?
Can you do cosine t squared by parts?
Yes, you could.
Are you sure?
Not.
What are the parts?
Cosine t squared and dt.
Okay. Okay.
That's on kids now.
You know what's
All
bad
right.
when the teacher asks you a question to answer your question?
All right. So anyway, so they like to give you problems where you can't anti-differentiate them easily or at all, right? In that case, what instead the strategy for you to use, and this is the strategy I want you to just build the habit of using, is just use a definite integral. Because if you have a calculator, and all of these problems are calculator, if you have a calculator, you can do a definite integral. Your calculator can always do a definite integral. Even if the function doesn't have an antiderivative, it has area. So you can always do a definite integral. You can't always do an indefinite, but you can always do a definite. So here's what we know. I know that the integral from 1 to 2 of velocity, we're talking about the x-coordinate of the velocity, or the x component, the antiderivative of that would be position, the x of t, from 1 to 2, or x of 2 minus x of 1. I know that x of 1 is 3, right? This is x, y. So I know x of 1 is 3, so I can plug a 3 in, and just x of 2 equals this, plus 3. Another way to think of it is definite integral of velocity is displacement. I don't know if you guys remember that or not, but definite integral of velocity is displacement. So what it says is, say I have a displacement of, I'm just going to make up a number, say I have a displacement of 7. I started at position 3. I since then have had a displacement of 7, so I do my 3 plus another 7, now I'm at 10. So I'm taking whatever the displacement is and adding the initial position to get my next position. It's another way to think of it, right? But what I want you to keep in mind is when you need an antiderivative, whether it's for position or whether it's for some other type of function, because a lot of times they'll do this in those antiderivative word problem kind of things too. So if you need, I don't know, like dollars, say you have dollars per hour. This company makes, you know, $50 million a day, whatever, and you want to know how much money did they make on December 3rd. Right, so that kind of a thing where you need an antiderivative at one spot, think definite integral. Definite integral of the derivative, because then the antiderivative will give you those values at those spots, right? Okay, so you do this. I want you guys to make sure you know how to do this definite integral from 1 to 2. So go ahead and get out your calculators, take a second, and do the definite integral from 1 to 2.
This is Christ. Does it matter what mode your calculator is in?
By the way, and a lot of people have asked me that today, I did 100% of the problems today in regular function mode. 100%. I used X instead of T, but it's, the math is the math, right? So I did the whole thing in regular function mode and was fine. Yes?
I forgot my calculator at home.
You wanna borrow mine?
Yeah.
How do you plug in V of t?
Well, you have to plug in what it is. By the way, which function do we use for our velocity?
Cosine.
Why just the cosine t squared? Because we're just talking about the x coordinate, right?
Oh.
Yeah, so you're just using cosine t squared for your velocity. So are they used to an 89?
Yeah.
Okay, good. Because I think I have some 84s too.
That's right.
Yes.
I got 4 instead of
8 degrees.
Whip from where?
2.
Oh, make sure you're in radians.
Oh, right.
Radians.
How do you know when to switch?
You,
Well, if you're in
everything
calculus,
calculus is 100% radians.
and almost everything in physics is not.
I have taken every published AP exam and I have never once seen a problem with degrees.
A lot of our,
Yeah, your book likes to use degrees.
Why don't we get a different book then?
Yes,
Yeah.
but the College Board is always radians.
This price, if our book does it in degrees and the College Board does it in radians, why don't we find a book that does it in radians?
Your book uses radians too. They just mix.
Our book is.
They do a nice blend. Right,
Actually, that's
I like to do a blend.
But no,
Here you for both.
I was.
but
You
life
know why, Brian? Because life has both.
Good one.
Yep.
And it's all about your
I
life.
suppose, although, like, in application, I think that you see more degrees in life than radians.
That is true.
I mean,
But the calculus is actually based, all of the derivatives and integrals in calculus are based on the concept of radians.
yeah, radians is a lot more helpful with a lot of the theoretical stuff we do.
Yes,
In physics, you use degrees almost exclusively.
yes. And in physics, everything's in decimals, right? And you guys do.
Yeah, for the most part.
Yeah. Everything is rounded. I never liked rounded. Someday, someone's gonna ask me for the square footage of my home, and I'm gonna give it to them in an unrounded answer, right? Like 482√3, and see what they say, right? That kind of.
That probably just roll their eyes.
That's a small town.
I know, I'm.
That's
That is a
that's like an apartment.
Is it even?
I think it would. I mean, that would
That'd be
probably
a
be
little
about
house.
600,
It's a
700
Little
square
house.
feet. 600 to 700 square feet. That's probably a large apartment.
Okay, okay, so did everyone get this? Are there any questions on part A? Okay, let's walk through part B. We're walking through these together. We're walking, just so that, you know, you get a comfort level. I'm not gonna let you do it on your own yet, but you will get to do it on your own, don't worry. Okay, for 0 to 1, you're not
I
worried.
like doing it together.
You know, why don't we do everything together?
For 0 to 1, there is a point on the curve at which the line tangent to the curve has a slope of 2. At what time is the object at this point? So we need to find the time when the slope of the curve is 2. How do we find slope of the curve? dy dx, right? So I need dy dt over dx dt. Stop kicking the camera. Alright, so do I have a dy dt and a dx dt?
Yes.
I do. That's your velocity vector right there. dx dt, dy dt, right? So it's literally just this over this. Where does it equal 2? I want you guys to find where it equals 2. Remember, you have a calculator. Use your calculator. Don't try to find it by hand.
What if you want the challenge?
I don't want, take the challenge, do the challenge on your own time, but don't do it on AP calculus practice test. Plus, I need to make sure you all can solve an equation with your calculator. Here, JJ, I have 84s over here.
I can use that. I know how to do the reason I didn't really worry about it was because I'm very certain I know how to do it.
Good.
Although I like the 89 solve function.
I know, isn't that nice? I know.
Yeah.
I love an 89 for solving equations.
I like the 84 Z graphics. Like, the way it sets up that is nice.
My grandma gave me an 81, I was like, thanks.
We had 81s at my old school. We still have class.
Yeah, it's from.
What is an 80, like, is that even a,
This is a.
No, there is 86. I had students that had the 86. I hated the 86. Very different looking. It had, when you like went to your graph window, it didn't have these buttons. It had like choices on the window. It was really weird. I didn't like the 86. No, I don't know. Maybe those were like versions that they tried and failed and they were flops. You know? It's like Formula 409. That, you know, the disinfectant or whatever, the spray, like, do you remember, like, Fantastic, you know, the spray? You guys don't know the household cleaners?
I know.
You guys not clean your houses?
I know what you're,
Use those Clorox clean wipes now, the newer stuff, I think that's still new. Back in the old days, we sprayed from a bottle and used towels.
I do that occasionally.
Okay, so one of the common household sprays was called Formula 409, and it was called that because it was the 409th try of getting the formula.
That's just such a cop-out, like, it's the same with WD-40.
WD-40?
That's good at getting duct tape off walls.
Oh,
It's good at oiling squeaky doors.
Okay.
WD is water displacement, and it was the 40th iteration of the, and I'm like, I look at that and I'm like, you spent so much time on this product, and then you couldn't even bother to come up with an actual name for it. Like, you
Oh, I
just,
kinda like it though.
Everybody
Rolls
knows
right
what
off the tongue,
WD-40 is.
WD-40.
There are 60 88s in existence.
Oh,
And they have the names all over.
really?
Yeah.
I wonder if they're like worth something.
They're from 1982, I don't know.
I always wondered if the number corresponded to the year, not the version. But it doesn't.
The
Okay.
TI
That's
Force came out in like 2011, 2012.
Okay.
Oh my god.
of course he knows
All
that.
right. Okay. So for part B, so you set your slope equal to 2 and solve. I will show you the answer to that in just a second because I don't have it written on here. So part C. Find the time at which the speed is 3. So, how do we find speed? What is speed?
Acceleration.
No.
Magnitude.
It's the magnitude of the velocity. It's the magnitude of velocity. So, speed is the square root of this squared plus this squared. Right? We want to know when the speed is 3, so you just do square root of this squared plus this squared and set it equal to 3. Speed is the magnitude of velocity.
Wait, what's
You don't need to integrate it.
I know, but technically could we?
What'd you get for
Not
B?
for this, but if we wanted.
Why are you trying to integrate it?
Well, no, I don't.
Just want to.
I don't want to, but is it the same thing? If you integrate velocity, doesn't that give you speed?
No, that's position.
Okay.
Speed is not a derivative or integral of anything.
Okay.
It is literally just the length of the velocity function, the vector. If we're talking vectors, velocity is a vector, speed is a scalar, right? So speed is just a number. It's the magnitude or length of the velocity. In function world, speed is the absolute value of the velocity. So. How many decimals do you need to make sure you're accurate to?
When is it 9? That was a Mr. Thomas thing? Yeah, that was that.
That was when we were doing error to, because you had to have it to like point zero, whatever, 0, million zeros and a 1, so you had to go way out.
Oh, only 3. I'll cut back then.
Yeah.
You've been using 9.
No.
I've been using 4 and just thinking that.
Okay, that's not correct. That's not.
Okay, once you have your answer for speed, the last thing we're going to find is total distance traveled from 0 to 1. Distance is the integral of the absolute value of velocity. When you're working with vectors, distance is the integral of the speed. Yes, Dylan?
Wouldn't B, don't you need like a number for that though?
Yeah, I told you, I haven't written the actual answers. I'm gonna pull up the actual answers in just a minute.
Okay.
Oh, so 3 isn't the answer.
No, that was the question. When is it 3?
Okay.
So that's just.
Yeah, I haven't, guys, I'll show you the answers in a second. I'm just kind of getting you walking through the setup and then we'll check in just a
Okay.
second. Okay, so last part. Find the total distance traveled from 0 to 1. So distance is the integral of your speed function from 0 to 1. So see if you can find distance. Yes?
Do you have an extra calculator? Just
Oh, sure.
Thank you.
Sorry to be anything with the battery.
Brian, what'd you get?
Looking on the calculator.
Oh,
I like to write out the full set. It's just me.
Total distance traveled from 0 to 1.
Because speed is also the integral speed is the same as the integral of the absolute velocity.
That's called the transitive property, right? If this equals this, and this equals this, and this equals this. Yeah.
Hey, camera. I'm in the extra.
This is Scott. Way confusing. I was trying to tell myself that it was first hit.
Guys,
Words of like used.
Hey, just to bring back old times for a minute, because someone was asking about distance.
Never. Like,
Way back when. Do you guys remember when we used to graph velocity? And we'd say, hey, here's a graph of the velocity. This area is 5, this is 3, this is 2. And I would say, oh, what's the displacement? And you would all say, oh, it's 4. What's the distance? Oh, it's 10, right? So the displacement integral, the integral of velocity, just raw velocity, which keeps the positives positives and the negatives negatives, that gives you displacement. But the integral of the absolute value of velocity, if you were to pop that 3 up there and do the integral, that's total distance traveled, right? Remember guys, velocity, positive, when we were doing horizontal, positive right, negative left, right? So this would go 5 to the right, 3 to the left, 2 to the right. But if you're talking total distance that your feet have moved, you want to add them all together. So that's why distance is the absolute integral, the absolute value of velocity. And hey, what's the absolute value of velocity? It's speed. So distance is the integral of speed. How's that for? Okay. All right. Yes, Carrie.
For the absolute value, the absolute
You don't need an absolute value here.
I know, but like.
Oh, if you were doing distance, like the actual absolute value of velocity integral, you put your integral in and then you do your absolute value and you put the velocity function inside of it. Not on the outside of the integral, on the outside of the integrand, the
So
function.
after the.
So you have
well, think about it.
integral absolute velocity. Because if I just did the absolute value on the outside, I would just get like my normal integral and just make it positive. I need this stuff to be positive before I integrate,
Okay, yeah.
right? Okay. Good questions. All right, so let's take a look at the, wow. Okay, let's take a look at the answers. Whoa, don't let
Let's
me.
take a, it's attendance.
Yeah, I know.
Guys, don't figure out who's gone.
Okay. So part A, 2.556 or 2.557. Okay, we're checking our answers. Part B, the time was 0.840.
Wait,
Really? You didn't, that was when the slope was equal to 2.
how do you solve that on your calculator?
Oh, okay. If you don't know how to solve on your calculator, if you have an 89, use the solve feature, right? So nice. Okay, if you don't, just go to y equals, put this like this in y. There's two ways to do it. Some people like to just put this minus this and then find the zeros, right? Some people like to put the first equation like that in y1 and then that in y2 and find the points of intersection, right? Either way.
That's pretty clever.
Yeah, but they're usually on an 83, 84, the easiest way to solve is to graph and then and then either graph both and do points of intersection, or graph set them equal to 0 and then find the zeros.
I still don't know what the solve feature is though.
No, that's all right. Do you have an 89?
Yeah, I do.
Okay, then, here, well. Oh, let's get you out of this mode.
Oh, it's in radians.
No, it's not, yeah, polar. Okay, but before we do that, all right, so solve. So we go up to solve, and then you type your equation in. So divided by problem with cosine is that there's multiple answers equals 2. So you literally just type the equation, comma x. You have to tell it what you want to solve. Close the parenthesis. I'm going to do diamond enter so I get decimal answer.
Yeah.
And it's thinking.
I never did this until now.
Yeah, it's still thinking. Okay, and there's the answer right there. It's the first one. Okay. Solve, it's always easier on the 89 to use solve than to do the whole graph thing. All right. Part C. Did you get a time of 2.196? Okay. And then part D, did you get a distance of 1.595? Yes? Good. All right. Excellent. All right, let's move on to the next one. All right. This next problem actually kind of bridged polar, parametric, PVA, and vectors all together into one big problem, right? I have this as a handout, but I'm going to start you on it before I hand it out. So let's just read a little bit. This was 2013, so we're just going back a couple of years. The graphs of the polar curves r equals 3 and r equals 4 minus 2 sine theta are shown in the figure above. The curves intersect when theta is pi 6 and 5 pi 6. They gave you the points of intersection. Yes. Okay. All right. So, part A. Let S be the shaded region that is inside the graph, both graphs basically. Find the area of S. Right? So they're asking for the area of the shaded region. So I have these hard copy along with 2 more problems. I'm going to hand these out, but I want you to start working on part A while I'm coming around. Yes. I apologize right now for the tiny font. I know it's a little hard to read. Yeah. Should we do our work on the way? Do wherever you want. Okay, by the way, this says homework. This is not your homework. You can cross out home right now and put class because we're doing this in class. Woohoo! Woohoo! No. And as a matter of fact, 11.1 you can just kill because it is no value at all to what we have. No, you have a huge homework assignment. It's going to be a handout.
Yay.
Yeah.
Okay.
Okay.
Calculator
I did an integral for the circle and an integral for the cardioid. Yeah. the funky weird looking thing.
Yeah.
Alright, sure. The font's not that bad.
Yeah, so I'm gonna bring well.
How do you do that?
2 quizzes in
Instead of,
I've never
I know
tried.
one
Wait.
I'll do
Try
it
doing
like
that.
Shut up.
over
Yeah.
6, and I
Zero,
know
comma,
it's
zero, comma, one,
something.
it didn't work, yeah.
I
I've
don't know
never
what to do.
tried,
Well,
so
you
I
put
don't.
the R would be the 4 minus 2 sign.
Yeah,
So
that's what I was thinking.
Why is
you
it
just
not
put that in.
But should I calculate,
Calculator or no calculator?
all calculator, these questions are all calculator,
no,
every single
Dylan.
one of them.
Wait, how do you
shouldn't you
how do
subtract out
you-
the 3 as well?
Okay,
Because, I mean,
I have to go run and get the
because if you
but
technically
yes.
are going from pi 6 to 5/6, you're gonna go all the way down here, or something like that.
Why do you want to do this?
Well,
Yeah, you're also-
No, because you do pi to, if you do pi over 6 to 5 pi over 6, what it'll do is it'll take from
Show me on the picture,
one
what are you
point
finding?
from the
Why are you wearing
here
my
of the light
bag?
from here, and it'll come around to that section.
Be more
And then
specific,
we
how
have
about
to add
starting
on
and where you're
to go
going.
from 5 pi over 6 to pi over 6 of the circle.
So why would you need
Or
those? You
5
never
pi over
have.
6 to 7
Well,
pi
okay, so
over
I divided this in half.
So here.
That was a good one.
And then I'm trying to divide.
Oh, okay, yeah.
This is it. Basically, you want to split this up into 2 sections. Here, so you have this section.
Cancel out.
Yeah.
But it doesn't matter, you're, okay.
So to give
I
this
think
section
you're not
pi over
understanding how
6,
to
which is
area.
here.
You're asking me the right? They told you this point is 5 right? Okay, so you're not, like, the only time you need the poles is
If she has time to turn around,
beginning or
So that would just be the area of the section.
area. You don't have one here.
Yeah, so you can ignore this part for now, so this would be the integral from pi over
So
6.
we don't want it, but they want here, we want it here.
I've had but then you also
Give me
need
this
this
number.
area here,
Yeah.
which would be 5 pi over 6
So
to,
for the circles from
which
0
would be equivalent to 7 pi
If
over
you
6.
were doing it this the way that you're doing it, yes.
So not 7 pi, not sort of 13 pi over 6. Then you do 5 pi over 6 to
Well, try putting the pi halves
Yeah.
into your cardioid and make sure that you really are at where it's got the line.
No, I separated it by, I just took this half. That's because I know that's and then I just found the integral here, here.
Wait, what did she say? No lie. Yeah, she said no lie should be nice.
They gave you the points, so okay, just go pi 6 to 5 pi 6 and then there you go. I mean, there's so many ways you can divide by 2 if you only want half these. You know, just like, they've given you these points, you don't ever need any of these others. You're making the problem harder by trying to do what you're doing. If you just do pi 6 to 5 pi 6 and cardio, you got that. And then do 5 pi 6 and circle. Because you can't go pi 6 because you're going backwards. So you have to go 5 halves or something like that. Or 0 to 5 pi 6 or 5 pi 6 to pi, whatever.
Why are you doing that if you go
He's a cartoon character.
Because you're going high to low. You have to go 5 pi 6 to 13 pi 6 if you're gonna do that.
can you do to 5 by 6?
No, because that would go this way. You have to go in the right direction, right? So that would be this part. It has, remember, everything in gradients goes this way, goes counterclockwise.
Okay. I have a question.
Yes.
Okay, so
I can't get out.
you find it, so when you do the integral from here to here,
Uh-huh.
so then that's why you do the cardio,
Yes.
cardio to this, and then are you gonna do here?
You could
So
go
then how do you find-
here to here and double.
Yeah, so but you can't go here to here.
You can,
Oh.
it's just that you need to use an appropriate angle, bless you.
Yeah,
Yeah, that's what I was just telling
but
Carrie.
if it's on your calculator, would it figure it out for you?
No. You need to use an appropriate angle.
Okay. So
If
then
you plug in pi 6, it's not gonna convert it to 13 pi 6, it's gonna be pi 6, it's gonna be.
oh, no, I meant, no, No, I didn't mean that, I meant like,
Yeah,
I get what you mean though.
like if this is pi 6,
Yeah, so you just,
and this is 5 pi 6, I can't type in my calculator 5 pi
Yeah.
6 to pi 6 because I'm going high to low. You gotta do 13 pi 6. But what's easier for me is 2 pi 6 to 3 pi halves and then double it.
yeah, but I mean, if it's on a calculator, it's really,
Yeah, because if you put pi 6, you'll be wrong.
no, I know, if you put 13.
Oh, well, then it's fine.
Okay.
Yeah, as long as it's correct, it's correct, yeah. 13 pi 6 will be fine. My thinking though is that a lot of students won't figure out to change that to a 13 pi 6.
What'd you get?
24.709.
That's unfortunate. I got 15.2 something.
Oh,
That's not the
okay,
same.
so when you do definite integral of, what's your function that you're doing?
I searched it, but it's like,
See, what if
Okay, so, oh, why did you like, did you square it out yourself? No, just.
well, I forgot I was a calculator problem.
Oh.
you got an eraser?
X, okay. 0 minus 2x squared. Okay, so you put your function, comma, x, comma, lower bound, so pi 6, comma, upper bound, 5, pi 6.
Okay, thank you.
Okay, see, do you know, I honestly, what I think is easier than doing the FN int, I personally like to do this. All squared. I like to put my function in the graph window.
Oh, did you remember the one hat?
Are you ready?
I don't know.
Okay, that last answer was wrong, because you were in degrees, you gotta be.
Wait, what'd you get? What'd you get?
24.709.
3 squared minus.
I put 9 pi over
And then if
6
you
instead
do
of
an
9 pi over
integral
2
here, you just go to your
for
Kaufman thing,
no reason.
integral,
Yeah.
and then it's gonna ask you for your lower limit,
Oh.
so, can you, I can't see,
Yeah.
pi over 6.
No, you don't.
And then your upper limit. And then it'll, yeah,
Okay.
but then you'd still have to times the half, I didn't put the half in, but yeah.
Alright, thank you.
Oh, I see what you're saying. Oh,
Okay.
okay, so.
So, lots of good discussion on this one. Let me get the answers up.
Yeah.
Now, they did geometry for the whole circle part. I didn't. I did it with integrals. So it's up to you. Because you can do it geometrically because the two little portions, like to pi 6 over here and over here, right? We know that's 1/12 of a circle, so the two portions would be a sixth of a circle, right? So you could do it with geometry, but you sure don't have to. I did this with integrals and then I did that with integrals, but either way you should get that answer. How'd you guys do?
I did get that answer.
You got that answer, good. All right,
I did the bottom half of the circle.
that's fine.
So you did the whole thing with?
I did the whole thing. Yes.
So you don't really need to split it into two integrals because, so like the boundaries or the starting and ending points, they don't vary for each of the integrals, or do they?
So, here, wait. All right, so you know that's pi 6, right?
Yeah.
And that's 5 pi 6. All right, so you can just go pi 6 to 5 pi 6 cardioid,
Yeah.
right? This one, symmetry is fine, but for the cardioid part, it's potato, right? You could go pi 6 to pi halves and double, right? This really doesn't matter. Okay, so that's the cardioid. The circle part, I think when I did it, I did 5 pi 6 to 3 pi halves and doubled. If you want to do it all in one swoop, you can't go 5 pi 6 to pi 6 because that wouldn't make any sense. You're going high to low. So you would have to convert this to the next, to 2 pi later, right? So you're going 5 pi 6 to 13 pi 6.
Oh, but the boundary doesn't matter since it's a circle. Like,
No, well, the boundary would
it
be
doesn't affect
3,
it, yeah.
right? 3 squared would be your radius, right? So anyway, either way. Yeah, so I did an integral for the circle and an integral for the cardioid. Good, other questions? Okay, so that's just old stuff. Let's move into new stuff. All right. So here now we're getting into the real, the real meat. A particle moves along the polar curve r equals 4 minus 2 sine theta, so that at time t seconds theta is t squared. Find the time t in the interval from 1 to 2 for which the x-coordinate of the particle's position is -1. Now, this is a polar equation. We want the x-coordinate of the particle's position. How do we write an x of t function from a polar equation?
Cosine theta.
Which one was it?
X equals cosine.
R cosine theta, right?
Theta equals.
Yes. So your x of t is r cosine, x of theta, sorry, we're in theta mode, is r cosine theta. You're given r, so your new x of theta function would be 4 minus 2 sine theta quantity times cosine theta. They're trying to change it to a parametric by telling you, hey, let's let theta be t squared. So now you change all your thetas to t squareds, and now you have an x of t function. Do you understand what they've done? All right. Okay. So
Sorry, no, keep going.
So you're starting with a general polar equation. That's the cardioid. We want the x-coordinate. An x-coordinate for this polar function, in any respect, would be written as r cosine theta. So you would write x of theta is 4 minus 2 sine theta times cosine theta, right? But we want a time t, so they said, hey, look, let's let theta be t squared. So now x of t would be 4 minus 2 sine t squared times cosine t squared. Yes?
Did you also find the theta where t equals, or where it equals -1 and then take this?
And then convert? You probably could, yeah, you could. Okay, so then the only reason that this is better is because you need this for the next part. Yeah. Okay, so we want to find the x-coordinates of the want to find the time when the x-coordinate is -1. So we're looking for when this equals -1. It's another simple solver. So you're solving again. Go ahead and solve.
Will stuff like this always be calculated?
Everyone I have seen so far has been calculated.
No.
What if this year they just
I
decided?
got them all regular.
Wait, is this PV right now?
This is kind of PVA because we're talking position right now.
Oh, okay, so we need to find, we have to find the P.
Yeah, we have, this is your x, the x component of your position function.
Oh, yeah.
This is x of t. X of t is your x component of your position function.
You said like you were gonna do a couple, and then like you do one by yourself, and then it would be done. I was like, wow, that seems really quick. This isn't going very quickly.
Also, a player for Jasper. No experience about that.
It's a dad band. It's a dad band. Yeah.
Are you
For nerds anyways. I'm a dad band.
Yeah. Did you join? Wait, you play the band?
Hey, what was that sound? There's like, the window, what happens weird rock.
Okay, check your answer. How'd you do? Excellent. Okay, any questions on solving? Alright, last little part on this problem. Okay, part C. For the particle described in part B, find the position vector in terms of t. A position vector is just x of t, y of t. You already have x of t. You just found it in part B. Now you need y of t using a similar process. Alright? So, find the position vector, which is just x of t, y of t. If x of t is r cosine theta, which is in this case r times cosine t squared, what is y of t? What's y of theta?
R sine of theta?
R sine theta, right? So you do r sine theta and then just change the thetas to t squareds. Is that okay? Okay, good. Last part of the last question. Find the velocity vector at time t equals 1.5. What you have written on your paper is the position vector. The velocity vector would be x prime of t, y prime of t, right? But you don't have to differentiate by hand because it didn't say find the velocity vector in terms of t. It said find the velocity vector at t equals 1.5. This you should do on your calculator. So, on your calculator, now personally when I do derivatives, I like to do them on the graph window, unless I'm on an 89, then I just do it on the main window. But if you want to use the f-deriv function, you can, it's fine. So what I would do is I would, in my y1, I would put my, what's x of t? So 4 minus 2 sine t squared cosine t squared. So I would do my 4 minus 2 sine, I would do x squared because I wouldn't be using the t button. 4 minus 2 sine x squared cosine x squared, right? And then I would graph, and then I would go calc, and I would choose dy dx, and I would then type a 1.5 and hit enter. And there's my derivative at 1.5. Yes?
On an 89, how do you get it to evaluate like a,
Oh, to evaluate, on an 89, if you wanted to plug the 1.5 in, yeah, you don't do comma 1.5.
yeah, because I could do like the 1.5.
Okay, on an 89, so you have your deriv, right? It's got your little, right? So you do, can I just write x of t for the function? Okay, so you do your function, comma x. On the 89, if you do like comma 2, it's going to do second derivative. If you do comma 3, it's going to do third derivative. So you do comma x, vertical bar, x equals 1.5, and it'll plug the 1.5 in. Vertical bar means plug this in. Yes? Oh, sure. Here, let me just back this up.
Okay, so let's read. I know it's I just plug stuff in.
No, it's one vector in terms of
I don't know.
right? how did you find this X of T?
Oh, I did our side, right.
Now you need a Y of T.
Do you know how
on
to?
the same kind of thing.
It's not doing that.
Sure.
See, I'm trying to solve the problem,
Okay.
but it doesn't want to solve
Got
it.
your
It's like, nah.
function.
Wait, where are you using
Oh, wait. So you evaluate the derivative first, then put vertical bar equals log
Possibly
5.
maybe a problem, but that shouldn't affect it.
It's not a problem, it's just an answer for B or B, but for C you do.
No, it's not
No,
asking
dude.
for slope, it's asking for a vector.
It's because we use
Vector
cosine, we multiply
is-
by cosine.
One side by
But
side.
it's not,
X prime, Y prime. Yes, side by side.
No, that's your point.
Yeah, you're,
Do you
whatever
want
you
the
want to
cosine?
plug in, even if I'm just saying, hey, 2x plus 5, what is this at
Like,
x
it's not the
equals
slope.
3, right? Just do vertical bar and it'll plug in.
So you're.
Yeah, you know when it works great? Great, when you have to plug in
the particle described in part B, find the position vector in terms of T.
and all that
Find the
stuff.
velocity
I
vector in
love
times.
plugging in and throwing that and just letting it. Yeah. Yes.
So for part B, I.
Are you going to do it?
Wait, you're building a race or anything?
No, I just.
Wait, are you two going? How much? Nah?
Dunbar.
Dunbar, hey, what's wrong with you? His name's Cole.
Your name's.
Oh, wait,
No, it's like an optional.
you have to put your, like,